welcome to our first webinar of this semester. And I'm really glad to introduce Professor Edson Sampaio from Universidade Federal de Ceará. We'll talk about the real version of the Theorem of Nobile. Thank you, Edson, for accepting our invitation. You may start and you are ready.
Thank you very much for the introduction, and thank you very much also for inviting me to give this talk. It's a pleasure to me participate here. Well, I think I cannot do everything that I want. I had a problem about sharing the file, but if you want, you can ask me. Maybe we can find a way to write something. I don't know how, but please stop me and ask me. Okay, I'll talk about this theorem. I have some initial considerations. The results present here are in the preprint real and by Lipschitz versions of the Theorem of Nobile. You can find it in my ResearchGate webpage. It's always well updated. And also in my archive webpage, and also in my homepage. You can find it there. I think it's good if you want to learn more about Lipschitz geometry. There are some papers there. You can find it. You can find them in my webpage. So if you don't remind this, you just search in the Google by my name and you can find. Okay, I will give some motivation and some introduction about the theorem that I want to talk about. For instance, the main tool here is the Nash transformation, which associates to a singular analytic set X the closure that I denote by Nx in X times the Grassmannian of the D spaces in the Cn or Rn. K can be R or C. And the closure is the graph, the closure of the graph of the Gauss mapping, defined outside of the singularities of X, arriving in the Grassmannian. In the well-known way, you associate a point to the tangent space. And then another, maybe here is better. The Nash mapping is the projection on the first factor that projects in X to X. And there are some important problems related with this tool that I arrived on this subject knowing this problem that I will talk now. The main problem, in my opinion, is the Nash sample conjecture. In fact, this is in the past was known as Nash conjecture, but nowadays, after they found the paper of sample in 1954, nowadays I think it's better to call Nash sample conjecture. The problem asks about if after a finite succession of Nash transformations of a complex analytic set X, this resolves the singularities of X. Another problem that is related with Nash transformation is a problem due to Ledun-Trung called Les duality problem. The problem posed that if the processes of resolution of singularities on the surface on the normalized blowing-ups, the Zarisk resolution, and unnormalized Nash transformation, the Spivakov's resolution, are dual in some sense. In fact, it's part of the problem to know what means dual here. In some sense, if you can find one resolution from the other one and vice versa, for example. And another problem that is related with this is related with Nash transformations is a conjecture posed by Javier Fernandez de Bobadilla about LNE sets. LNE here means locally LNE. If you can find a constant such that the geodesic distance is controlled by the ambient distance. Here, the ambient can be from some Riemannian manifold, not only Euclidean one, because I'm asking about LNE on sets in the Grassmannian, for example. So the Nash transformation, the problem posed asks if you have a Nash transformation of an LNE set, this is LNE as well. After you blowing up, after you transform by Nash transformation an LNE set, it asks if this is LNE as well. This is almost all of them are open except the first one, because there is, in fact, the first one is almost killed. The recent results of some guys from Chile and Mexico, Daniel Duarte, Liendo, Castillo, and Maximiliano, they almost solved this problem. In fact, I say some words about that. Some important contributions to the Nash sample conjecture. There are many contributions to this conjecture, but I will highlight only 3 of them. The first one is the Spivakov's contribution. He showed that the resolution of singularities of surfaces using normalized Nash transformations. And then recent results by Castillo, Duarte, Leuton, Alvarez, and Liendo. 2 papers, in fact, more than 2 papers, but mainly in 2 papers, provide contact example in all dimensions greater than or equal to 3. So the conjecture remains open only for d equal to 2. The other result is the Theorem of Nobile, which is central to the understanding the rule of Nash transformations in the singularization. It states the following: for a pure dimension complex analytic set, X is analytic, is smooth if and only if the Nash mapping is an analytic diffeomorphism. And here, analytic diffeomorphism means that it is analytic always because it's a projection, but the inverse exists and is also analytic. And analytic here means it's a restriction of an analytic function locally. No, this does not say anything about the existence of an analytic diffeomorphism. This says nothing about the singularities of X a priori, but by the theorem says that there is no singular set. And this was proved by Nobile in 1970. It was a complex analytic proof. Tessier, almost at the same time, gave a more algebraic proof. Nobile also proved that the theorem does not work in any positive characteristic. And Duarte and Nunes Bentecourt recently proved that the theorem of Nobile holds true for any normal varieties in any positive characteristic. There are many other contributions, but I don't have time to say all of them. But when I saw this problem, in fact, there was two natural problems on this subject. The first one is about the real version of the Nobile theorem. Does the real version of the Nobile theorem, particularly asking about CK smoothness, hold true? And the second one, this was an open problem for 50 years. And the second problem is, can the analytic diffeomorphism condition of the Nash mapping be weakened? So the aim of this talk is to provide positive answers to these two questions. Let me state the theorems. The first real version of the theorem is the following. If you have a pure dimensional real analytic set, so you can have CK X is CK plus 1 submanifold. This means you can find parametrizations which are CK and the derivatives are Lipschitz. This means CK plus 1, sorry. You can find parameterization which are CK plus 1, and the comma 1 means the K plus 1 derivatives are Lipschitz. This holds if and only if the Nash transformation is a homeomorphism, and the inverse has more or less the same regularity but less 1. The inverse is CK1. That means it is CK, but its K derivatives are Lipschitz. And another theorem is the exactly real version of the Nobile theorem. In fact, I prove even more. For X being an analytic set, pure dimensional analytic set, the following are equivalent. X is a real analytic submanifold. It's the same of eta is a real analytic diffeomorphism, which is the same at eta is C infinite diffeomorphism, and it's the same at X is C infinite submanifold. Just to say some words about how to prove this theorem 2 using theorem 1. It's easy to verify that 1 implies 2 and 2 implies 3 and 3 implies 4. In fact, 3 implies 4 comes from the theorem 1, because if at infinity means it is CK1 for all K, and then for the same reason X is CK plus 1 for all K, so X is C infinity. And 4 implies 1 is, you can use a result of Ephraim that who proved that two real analytic sets that are C infinity diffeomorphic has germs are analytic diffeomorphics. So the main problem is prove theorem 1, and the change here is to prove the theorem 1 when K is equal to 0. The other cases are more or less some argument of bootstrap argument. So another theorem is the real the Lipschitz and Hold versions of this theorem. In fact, I can I only need to ask the regularity on the eta. The only regularity that I need is the inverse has to be locally alpha Hilda for all alpha. Please note that the Nobile theorem, he asked eta, the inverse of eta is analytic, so it is in particular locally Lipschitz. It's the infinity in particular. So it's in particular is Lipschitz and also alpha Hilda for O alpha. But what I'm answering here is if it is alpha Hilda for O alpha, this also implies that X is a submanifold also. You can, in fact, I showed this is the sharp condition. You cannot ask less than this also. As a corollary, we prove that the X is smooth if and only if the eta is a homeomorphism locally by Lipschitz. Okay, let me see if do you hear me? Just to verify if I'm not.
Yeah,
Okay.
okay.
Just, thank you. Okay, so let me continue. In fact, everything I could find a proof that works even in a much more general setting, which is the setting of locally definable in all minimal structures on R. And I could even put here A equal to 1 or equal to log Lipschitz. I did not define log Lipschitz here because I thought I could write, but I cannot write here, so you can search what means log Lipschitz. So I proved that X is CK plus 1 A, and A here is 1, which means Lipschitz, or log Lipschitz, which is weaker than Lipschitz. If and only if C3 and C4 coincide linearly, I will define what means just in the next slides. And the eta is a homeomorphism, and the inverse is Ka. Here, in the last theorems, A was 1, because in the last theorems, I was dealing with analytic sets which are locally definable in an omnimal structure, which is polynomially bounded. And then any log Lipschitz is Lipschitz in this setting. So let me say some preliminaries, because many of you maybe don't understand what I said in the theorems. Sorry. Let me remind what means omnimal structure. For me, is a collection of SNs. Each SN is a subset of the parts of set part of Rn, such that the algebraic sets are in S. It is a Boolean algebra. That means intersection, union, and complement of two sets there is there. Cartesian product of two sets there is there as well. Projection of a set in Sn plus 1 is in Sn. And the unique sets which are in S1 are finite union of intervals. So this means omnimal structure. If you don't understand this definition, a very easy example of omnimal structure is the collection of all semi-algebraic sets. In fact, the minimal one. So in this case, I will call a set A in S. I will just say definable in S. And I will say A is locally definable if for each P in A, there is some neighborhood of P such that the intersection is definable for some neighborhood. There are some sets which are definable, locally definable, but are not definable. For example, the graph of the sin function, for example, or cosine function, also. So the collection of semi-algebraic sets is a non-minimal structure, as I said, and any semi-analytic set is locally definable in some omnimal structure. That's all you need to know. So tangent cones for me is I will need only two definitions of tangent cones. The third one and the fourth one, the Whitney tangent cones. The third one is I will denote as C3xp, which means the tangent cone of x at P is the set of all tangent vectors at P obtained has secant vectors. That means all V's such that there is a sequence xj in X and a sequence tj of positive numbers such that this limit holds true. And for definable sets, C4, the fourth tangent cone of X at P consists of all the limits of tangent spaces at smooth points approaching P. At a smooth space, a smooth point, you have a tangent plane. And then when we approach to this point of us in the singular set, we have a sequence of tangent space. After taking subsequence, for example, this tangent space converges in the Grassmannian for some T, some plane T. So you collect all of this T. This what I mean C4 of X at P. In general, for definable sets, always we have this inclusion. C3 is including C4. And I would say C3 and C4 coincide linearly if they are equal whenever C4 is a d-dimensional linear subspace. And D here is the dimension of X. Example of this property is any complex analytic set has the property C3 is equal to C4 linearly, because it's well known that the C3 for a complex analytic set, C3 is an algebraic set of the same dimension of X. So if it is inside of a d-dimensional subspace, linear subspace, and this the dimension of X, the C3 has to be this space, this subspace, linear subspace. Okay, so this I think is all the definition that I needed. The notion of tangent cones, the notion of coincide linearly, and the notion of definable and locally definable in non-minimal structures. And also we needed Lipschitz definition of Lipschitz or Hilde and log Lipschitz. I did not write here, but you can search quickly. You can find the definition on the internet if you want, if you don't know. So again, the theorems and applications to the theorems. Here for a locally closed d-dimensional set, which is locally definable in a all-minimal structure. X is a CK plus one submanifold if and only if C3 and C4 coincide linearly. And eta is a homeomorphism, and the inverse is CK1 smooth. I will use only this. I give some hints of the proof only in this case, when A is equal to 1. The proof is slightly different when A is equal to log Lipschitz. And for sure, when I will also obtain X is same infinity submanifold, if we obtain C3 and C4 coincide linearly, and the mapping, net mapping, is a same infinity diffeomorphism. So I need two lemmas to import lemmas. For instance, if you are in the case of X is a real analytic set, if eta is a homeomorphism and the inverse is C0, 1 smooth, that means locally Lipschitz. Just another. This is just another way to say eta. The inverse of eta is locally Lipschitz. Then C3 and C4 coincide linearly. Just to with this lemma, I cannot apply theorem to prove the theorem 1. Theorem 1 is the exact theorem, more or less the theorem for real analytic sets. And the other lemma is for real analytic sets, we have that locally for real analytic set, it is locally definable in an all minimal polynomially bounded structure. So in this case, if eta minus 1 is alpha Hilde for all alpha, we have Loyachev inequality in that case. So if some function which is definable in a polynomially bounded structure, and it is alpha Hilde for all alpha, this implies, in fact, this is Lipschitz. This is why I will prove only the Lipschitz version. But the alpha Hilde is the log Lipschitz is harder. Okay, so it's as a consequence of the theorem, it's easy to obtain, and the lemmas, we obtain this theorem 1. It's a consequence, immediate consequence. And also, as I explained this, we obtain also theorem 2 as an immediate consequence of theorem 1. And for sure, we also obtain the theorem, the version for complex analytic sets, because any complex analytic set is a real analytic set. So you can apply theorem 1 for the corollary to obtain, for example, if eta minus 1 is locally alpha Hilde for all alpha, this implies eta is Lipschitz, eta minus 1 is Lipschitz, and then this implies by theorem 1, X is C1, 1 is smooth. But if X is C1, 1 is smooth, it's locally X is graph of C1, locally the graph of a C1 mapping, and then X is smooth, because you can show this mapping, which is giving the graph, is in fact holomorphic. This is well known. I think the first person that proved this was Milner, but this is well known. So this is an easy corollary of the theorem 1. So let me spend some time before to give some hints of the proof, showing the sharpness of the hypothesis of the theorem. For example, we cannot expect the same theorem asking less than all alpha Hilde for all alpha. You cannot expect obtain a theorem for alpha Hilde for all alpha less than some alpha 0. Because I can find this example for any alpha, I can obtain some k such that k over k plus 1 is bigger than alpha, for any alpha less than 1, for sure. Take alpha less than 1. And then I can define this yk, defining this way. And then we can show this is a homeomorphism, and more than is a homeomorphism, this is the eta is always Lipschitz because it's a projection, but the inverse is also alpha Hilde for this alpha if alpha is less than k over k plus 1. But this set is not C1 smooth. In fact, it's not even a topological manifold. As I think it's not C1. In fact, so only ask C0 alpha smoothness is not sufficient to guarantee smoothness of X. So you cannot obtain a weak version only asking less than alpha Hilde for all alpha. Another problem is we can obtain examples where the Nash transformation is B alpha Hilde homeomorphism for all alpha. In the omnimal case, because in the real analytic case, as I explained, if it's B alpha Hilde for all alpha, it is by Lipschitz, the Nash mapping, because it's definable. It is definable. But in the definable case, you cannot obtain the same theorem as I obtained for real analytic sets, because for real analytic set I stated for the regularity that I asked was alpha Hilde for all alpha, but for definable sets I only asked Lipschitz or log Lipschitz. In log Lipschitz, alpha Hilde for all alpha, for example. And the example is the following: is please remind that there is something like that. We can show the. I think I put some picture here. The graph. We just we have two functions which are C infinity, and they are tangent here. In fact, the tangent is very high, but in fact, X is not a topological manifold, for instance. And in fact, you can prove that the Nash mapping is a homeomorphism. In fact, it's a B alpha Hilde homeomorphism for all alpha. And in fact, you cannot obtain even that X is a topological manifold. So Hilde regularity fails. In fact, who knows what means log Lipschitz? We have a notion of gamma log Lipschitz, and all log Lipschitz, in fact, log Lipschitz is just one log Lipschitz. And we could ask about the theorem for gamma log Lipschitz, and in fact, we cannot ask that because the theorem also does not hold. For any gamma, I could find examples where the Nash mapping is a gamma log Lipschitz, B gamma log Lipschitz, and the set is not C1 smooth. In fact, the set is not topological manifold. The graph is more or less the same. I did not put the picture, but the picture is very similar to this one. The difference is because the tangents here is even high. Here, the tangents here in this example is even high because here I put M. In fact, I can for any gamma I choose gamma greater than 1, I choose some m that this inequality holds, and then I can show the Nash mapping of this guy is gamma log Lipschitz when gamma satisfies this inequality. So you cannot expect the same theorem for gamma log Lipschitz when gamma is greater than 1. So the theorem is sharp. You cannot, about the regularity of it, you cannot expect less than this. But also, we cannot drop the condition of C3 coincide with C4 linearly. For instance, you can obtain the epigraph of the cusp, for example. And in that case, which is these are a region, the closure of the open set in R2, so that the C4 is are planes are R2 in any place. So the inverse, the second coordinate is just the limit of set, in fact, is R2. So this mapping is a C infinity, but for sure this is not a C1 manifold. In fact, it's not a C1 manifold if with boundaries, not. So you cannot drop this condition. Another condition another interesting example that I found was the following. Just an example that you can obtain an example where the set is, because here the set is not a topological manifold, but here you can find even a set which is a topological manifold. It's gamma log Lipschitz for all gamma greater than 1 plus 1 over m, but it's not C1 manifold. Just now to finish my talk, I will give some outline of the proof of the theorem. In fact, I want to give some hints how to prove this theorem. I waving hands a lot, in fact, but it's what I have at this moment. So again, the main difficulty is the implication, the converse of the theorem, in fact. But let me say, I already stated this theorem twice. Someone want to ask something?
No.
No? Sorry. Okay. So this direction, we can prove this direction using plug embedding. Just to say some words about this, when you have that x is ck plus 1, 1, when where k is a non-negative integer number. In fact, in this case, x is at least C1, 1. So, in fact, x is at least C1. When x is C1, you can write x as the graph of a function which is C1 locally. And then you can see the Nash, the inverse of the Nash mapping, and then you can take the plug embedding, and you look here, the embedding here, the plug embedding, and you look at the coordinates of the embedding. The plug embedding is algebraic, so in particular C infinity. So when you look the coordinates of the plug embedding, here appears the partial derivatives of the map that is given the graph. X, let me say x is the graph of a function 8, for example. So when you look the image of eta, or image of eta, and then the plug embedding. Here appears the coordinates, and the coordinates appear. Part of the coordinates are the derivative of h. So if you assume that x is ck plus 1 and eta is ck, so we obtain the derivatives are ck as well, because when you compose ck and c infinity, and here appear the derivative, so the derivative is ck as well. So it's because eta minus 1 is ck plus 1, and then you can use some recursive argument or bootstrap, something like that, and obtain the regularity that we want. Something like that. You have, I'm a lucky guy, so I will focus in the more intricate implication, which is the converse, when I assume regularity on the eta, and then obtain regularity on x. So let me assume, for example, eta is a homeomorphism, and the inverse is ck1. I want to show x is ck plus 1, 1. Just to begin, let me assume, firstly, k is equal to 0. So we have to prove x is c1, 1. In particular, k equal to 0, this means x is a homeomorphism and locally by Lipschitz. So assume by contradiction that x is not C1 for start our proof. And then using the techniques developed by Kurika, Legal, Nyam, they prove that in the situation that I'm here, the tangent cone, I can show, for example, the tangent cone here is a linear subspace in any point and varies continuously. You can prove that. And in that case, if x is not C1, this means that there is some projection to the tangent cone such that the projection is not injective. So take a point like that. There is a point P such that the orthogonal projection to the tangent space restricted to x is not injective near P. So because that we can find, it's not an easy task, but you can find some gamma in RD. I'm considering here RD, in fact, is the tangent cone of x at P. I'm assuming here P is equal to 0. Just I'm translating to the origin. And since C3 is a linear subspace of dimension D, I'm just identifying C3 with R3. So you can find some arc in the tangent cone such that it lifts to x via P by gamma 1 and gamma 2. We have at least 2 lifts because it's not injective. In fact, it's not for any gamma that we can find it, but we can find gamma in a very special way. It's part of the proof to find gamma in a very special way. And I will call G the difference of these 2 lifts. In fact, I can obtain these 2 lifts in such a way such that around each point of gamma I, x is the graph of a C1 function fi. Then, if you obtain this is the delta, is the distance in the Grassmannian. Okay? So, it's not hard to prove the distance in the Grassmannian here, since they are graph of C1 functions, there is some constant k such that we have this inequality. But what appears here inside of the norm is just the derivative of g respect of t. So we obtain that the distance on the Grassmannian at each of these points is greater than some constant g prime. And then I can use now that eta is by Lipschitz to obtain, for example, this delta is less than some constant. The distance in the Grassmann space using that eta is by Lipschitz. This is less than gamma 1, the norm of gamma 1 minus gamma 2. But gamma 1 minus gamma 2 at t is just g. So we obtain, for example, g of t, the norm of this is greater than some constant times the norm of the derivative. So, but here g is definable because there are lifts of definable sets. In fact, it's not true. Lift of a definable set is a definable curve is a definable curve, but the way that I obtain these two curves where I obtain a definable way. I can prove gamma 1 and gamma 2 were definable, in fact. So this is why G is definable. So if G is definable, we can, and G of 0 is 0. I'm assuming gamma 1 at 0 is gamma 2 at 0. We can prove this limit when t goes to 0 is 0. But this is a contradiction because when we divide by gt here, this is bigger than some constant, positive constant, cannot go to 0. And the contradiction comes from we assume x is not C1. Okay, there are a lot of big steps here, but it's more or less how to prove. The big steps are here. So we have a contradiction. So x is C1. So after we obtain x is C1, we can write now x has a graph, and you can use plug embedding to obtain that the regularity of that mapping that is given the graph is the same of x less 1. So we finish more or less like that. So I don't have many time to this because the way to increase the C11 is we have similar strategies, and as I explained, for k greater than 1, we have to use some bootstrap argument using plug embedding. I don't have time to this because my time is. Thank you very much for your attention.